So today we will discuss section 6.4 of entrance calculus, which is arc length, length of a plane curve, or sometimes we say arc length, length of a plane curve. Curves can be in space as well, but this is just a plane curve, means in two-dimensional. You see, previously in 6.1, we saw that if a curve is given, y is equal to f of x, uh, and we found the area from A to B. So if I have to find this area, it was simply the area problem in 6.1 was integral from A to B fx dx, right? So we have two options. This was in section, I think 5, in chapter 5 we studied that. In section 6.1 it was area between two curves, but anyway, uh, here we have two conditions on our function, that fx is greater than equal to 0 and f is continuous, right? So if two conditions are satisfied, we can find the area. Now, in length curve, arc length problem, we again have the same. Some curve is given, y is equal to f of x. But now we want to see if I travel on this curve, let's say if I start walking on this curve from here and finish at the last point, how much distance I have covered. So basically it is called the length of the plane curve. This is L now. Okay. So see, so in short, we can call it arc length as well. Length of a plane curve or arc length. Arc is also used for curve, right? So our problem is that a function is given. Suppose y is a smooth curve on the in the interval AB. Define and find a formula for the arc length L of the curve over the interval. So what is a smooth curve? So here my condition is smooth. It means my function and its derivative, they both should be continuous. Okay. So here fx is smooth on the interval AB. So smooth means, which means that f and f prime both are continuous. So why we are saying that f prime is a continuous function? Sometimes f prime is not continuous. For example, if I have a corner point, let's say, at a corner point, f prime does not exist, right? So it is still continuous. F is continuous, but f prime does not exist. F prime is not continuous there. So it means we should not have a corner point. So all the turns should be smooth. If my curve is turning, it should turn smoothly. It should turn smoothly like that. So this is a smooth turn, right? So there should be no short turns. So this is a corner point. So no corner points should be there. Okay. So corner point should not be there. So all the turns should be smooth, right? So anyway, if this is your function, most of the polynomials are all smooth functions, exponential, sine, cosine, these are all smooth functions. So we should not worry about that. So how to find the arc length? Let's say what we do is we pick a small piece. Let's say if I pick a small piece here, right? And zoom it, let's say zoom it, right? So it will be like this, right? This is your curve, the piece of that curve. I want to find that piece. So let's say it starts from x and go to x plus delta x plus h or delta x. Small change in x. This change in x is delta x, right? Or dx, we can call it. You can either call it delta x or dx, both are fine. Delta x, dx are same. Anyway, now if you complete this triangle type thing, this triangle, right? So this is dx, corresponding change in dy, or this is delta x, corresponding change in y is delta y. And let's call this as ds. Small portion of the arc length is ds. So see, it is kind of a right angled triangle. Okay, so ds square should be equal to delta s. We should not write. If I'm writing all deltas, then I should write delta s here. So that should be delta x square plus delta y square. From here, if I divide by delta x square, let's say divide by delta x square, so this will become 1 plus delta y by delta x square, right? And if I take the square root now, delta s by x will become 1 plus delta y by x square root. Okay, so here now I can bring this delta x over there. I can multiply it over there. So see, if I now you see here, this what I did is when I used Pythagoras theorem, I had a triangle dx, dy, and the straight line as ds, delta s. This was delta x, delta y, delta s, straight line. But my curve may not be a straight line. My curve may be a little like this, right? So see this red, this black one is the original length of the curve, but delta s is this light blue curve, right? So ds can be approximated by delta s. They are not equal, but if this delta x is very small, if delta x is small, we can approximate this. Let's say if I take a big portion of a curve like this, and now we are taking a straight line. You see, there is a big difference between these two. A straight line and this line, there is a big difference, right? Here, delta s and ds are not approximately equal. They have a lot of distance. But you see, when we have a small interval, let's say from here to here only, and if I draw a straight line between these 2 points, you see. So if delta x is small, here my delta x is big. If the delta x is small, this one, then there is not much difference between ds and delta s. So if delta x is small, then they can be approximated. Okay. And if I take the limit, right? So if I take the limit as delta x goes to 0, right, of delta s, then it will be exactly equal to ds. Okay, so here if I take the limit on both sides, that limit delta x goes to 0 of delta s, and here if I take the limit delta x goes to 0 of this whole thing, 1 plus delta y by delta x square. Okay, so if you do that, let's not take it over there, keep it here. And this is the derivative formula. If you look at this one, this is defined as the derivative of s with respect to x. And if I take the limit inside, this will also become 1 plus dy by dx square. So see, that's how we can find ds. So see, ds is equal to 1 plus dy by dx square root into dx. But this is happening only at one point. You see, if I take this x only, so and when I take the limit delta x goes to 0, right? Then this point moves towards this one. So at one point, I have estimated my ds. And we have to do it for all x, not just one x. So at one x here, I estimated this ds here, right? But x can go from left to right. So I have to do it for the whole interval. So it means I can just integrate. When you have to sum it up, I can integrate this one from A to B, this ds. If I integrate, which is A to B, 1 plus dy by dx square dx. So this gives me the actual length of the curve because I have added all these ds's from A to B. So now I'm getting all these points from A, getting all these points added up. We are adding up all the points from A to B. So this will give me the complete length L. Okay. So, but anyway, now this is the background of this formula. But from now on, whenever they will ask me to find the plane curve, of course, I will not do what I did here in the past here, because here I was giving you how we can make it a formula. Now we can just use this formula and find the arc length of any function. If a smooth function is given over the interval, I will integrate this 1 plus dy by dx square over the interval. So let's see an example here. So see, I can show you the formula which they got here, right? I wrote dy by dx, f prime dy by dx is the same thing, right? So if y is fx, then of course dy by dx is f prime x. So either you can write f prime here or dy by dx here, same thing, right? So now this example, find the arc length. Let me nip it from here. Example 1. Okay, so before doing there, let's say if you have there is another formula that if you have your curve, right, again, but you are getting the value of, let's say, y instead of x. Let's say your y is given. So if you take any y here, you will find this thing, which will be ds, right? And now y will go from this to this. But now when you remember, when y is taken as a variable, independent variable, then we write x is equal to g of y. Then we don't write y is equal to g of x because y is independent. So in this case, my arc length will become c to d, and ds will become 1 plus dx by dy. So it will be opposite. Instead of dy by dx, it will be opposite with respect to y. So remember here, this dx is down and we are integrating with respect to x, and x goes from a to b. Okay, and here y is down here and we are integrating with respect to y. So when we integrate with y, it should be dx by dy, and the values of y should be in the limit. Y goes from c to d. So you can change the formula accordingly if you are doing with respect to x or y. So see, in this example, he said do this problem in two ways, using formula 4 and using formula 5. So in the book, they gave you these two formulas. Uh, I can show you in the book. See, this is formula 4 with respect to x, formula 5 with respect to y. So he said use both in this example. So let's copy this figure as well. We can make this figure not an issue, but anyway, where is it here? So this is your figure. This one's figure. So find the arc length of the curve y is equal to x to the power 3 by 2 from 1, 1 to 2, 2. So see, x goes from 1 to 2, but y goes from 1 to square root of 2. So he said do it in two ways. So I have to only find the length of curve from here to here, this portion of the curve, not the whole thing, because he said from this point. So here x is 1 and here x is 2. So x goes from 1 to 2. So first of all, in A part, he said using formula 4, it means this is a formula 4 basically, this one. This one is formula 4 and this one is formula 5 when you do it with respect to y. So when I use formula 4, it means I have to find dy by dx first. Dy by dx. I need this. Y is x to the power 3 by 2. So it will become 3 by 2 x to the power 3 by 2 minus 1. That is the derivative. So 3 by 2 x to the power 1 by 2. So therefore, the length of curve using formula 4 gives you from A to B. A is from 1 to 2. From A to B, 1 plus dy by dx, which is 3 by 2 x 1 by 2 square, and then square root dx. If you want, you can find this thing separately and put it here if you want. You can simplify this outside the integral. But anyway, here you got 9 by 4x. 3 by 2 square will become 9 by 4 and square root of x square will become just x. So I got this one. Dx, okay. So here I can, you know that when there is some function inside the square root, I cannot integrate it directly. So we can use substitution, what we did in section 5.9, section 5.3 and 5.9, I guess both. We do this substitution method. Substitute u is equal to 1 plus 9 by 4x. Okay, and if this is the case, then du becomes 9 by 4 dx. The derivative of this is 9 by 4 into dx. But I only have dx. I don't have 9 by 4. So I can multiply it here. 4 by 9 du is equal to dx. So now you see this will become square root of u, because this whole thing becomes u. And this dx is 4 by 9 du. Right? So this is the value of dx. So now I should change the limits as well, right? Not just this one. The limits are from 1 to 2. These are the limits for x. If x is 1, your u is 1 plus 9 by 4 into 1. We have to put it here, right? If x is 1, then u is 1 plus 9 by 4. So that is 13 by 4. And when x is 2, then u is 1 plus 9 by 4 into 2. So 2 2s are 4. So that becomes 11 by 2. So my limits become 13 by 4 to 11 by 2. Okay. So these are my limits. Now 4 by 9 is constant. I can write it outside. 13 by 4, 11 by 2. And square root of u is 1 over 2 du. And now we can integrate it very easily. It will become u to the power 1 by 2 plus 1 divided by 1 by 2 plus 1, from 13 by 4 to 11 by 2. So now you can replace 11 by 2 here first. So 4 by 9. 3 by 2 can also be written outside. So this 3 by 2 outside will become 2 by 3, right? And u to the power 3 by 2. So 11 by 2 power 3 by 2 and minus, if you put this here, this is 13 by 4 power 3 by 2. So that is your answer. So 8 by 27 and whatever, you can just find that. Let me show you the answer here. This is the correct answer. So see, if up to here, I have the same thing. 8 by 27, 11 by 2, 3 by 2. 8 by 27, 11 by 2, 3 by 2, and 13 by 4, 3 by 2. So it is almost 2.09. So you can check that this is almost 2.09. So that is the length of the curve. So if I use formula, the other one, right? The other formula, so this was my formula. So from 1, 1 to the second point was 2 and 2 square root of 2, right? So now if I use y-axis as my integration. So my y is from 1 to 2. So this is 1 and it is going to 2 square root of 2, these limits of y. But now I will write this function as x, right? So my x is y to the power 2 by 3 because x 3 by 2 is y. So this 3 by 2 will become 2 by 3 on the other side. Power 2 by 3, right? So this is my x and y goes from, so if I take any y here, y goes from 1 to 3 by 2 and any ds, right? So my formula will become here. So L will become from 1 to 2 square root of 2 and 1 plus dx by dy square. So from here, from here, I have to find dx by dy now because my formula is dx by dy. So it is 2 by 3 y to the power 2 by 3 minus 1. So that is 2 by 3 y to the power minus 1 by 3. Minus 1 by 3. Okay. So here I got 2 by 3 and you can bring it down, right? It will become 2 by 3 y 1 by 3 square. And this is with respect to y. So you can check here. When I use the other formula, I have this, right? 1 plus 2 by 3 y to the power 1 by 3 square. So now if I simplify the integrand first, I cannot integrate directly. So this will become 4 by 9 y to the power 2 by 3 dy. So take the LCM, multiply it here. It will become 9y 2 by 3 plus 4 square root and divided by 3y 1 by 3 outside the square root 1 2 square root of 2y. Now what substitute? Now the derivative of this 2 by 3 is 1 by 3. So I can replace again. I can replace this whole thing as u, this inside thing. So now we can substitute u is equal to 9y 2 by 3 plus 4. And then du will become 9 into 2 by 3 y to the power minus 1 by 3 dy. So see, it is 1 by 3 y to the power 1 by 3 dy. And I can bring this 9 to the 18 on the other side because I have this thing here. You see, I have this thing here. This is my y, right? So we can replace it here. That's why I brought 9 into 2 on the other side. So now if I put it here, I will get square root of u, and this derivative is du by 18, right? This du by 18, and this thing was square root of u. And now we have to change the limits as well. So if I change the limits, when y is equal to 1, your u is equal to 9 plus 4, 13. And when y is equal to 2 square root of 2, then u becomes 2 square root of 2 is basically 2 to the power 3 by 2, right? So if I put this in u, you see you have 9 into y to 3 by 2 and power 2 by 3 plus 4. So see, these powers will cancel. So you got 18 plus 4, 22. So your values are from 13 to 22. Let's see here. See the same thing. 1 by 18, 13 to 22 is square root of u du. So same thing I got 1 over 18, 13 to 22 and square root of u. So now 1 over 18 is constant. U to the power half will become 3 by 2 over 3 by 2 from 13 to 22. So now it is 1 by 18 into this become 2 by 3. And if you replace 22 here, it is 22 to the power 3 by 2 minus 13 to the power 3 by 2. And this should also give you exactly 2.09 because we are getting the same arc length. It is the same function, same arc length. We are just using different formulas. Different formula should not give me a different answer. Answer should remain the same. Okay, so that was not that difficult. I just have a formula, but within the integration, we had to simplify this thing. So as I said, you can do the simplification part aside as well. Before integration, we can do that. For example, if I pick something from exercise, let's say, in exercise, we can use 3 to 8. So this is 3 is the same as I did in the example because it is 3 by 2. 2 by 3, we also did this. So they both are almost the same as in the example. I did one for 3 by 2 and one for 2 by 3. So these both are doable. So if you want, I can repeat one of them. Let's say if I do from exercises, try exercises 3 to 8 on page 441. So try anyone. So let me make an integral and then I can leave. You can complete the integral because you have done it in chapter 5 and 6. So y is 3x 3 by 2 minus 1. 3x 3 by 2 minus 1, and x goes from 0 to 1, right? So x is from 0 to 1. So whatever that is, I know the formula uses dy by dx. So my formula, I know I can write it from a to b, square root of 1 plus dy by dx square dx, right? So I can simplify this outside the integral if you want. So let's say dy by dx is 3 into 3 by 2 x to the power 3 by 2 minus 1 and minus 0. So that is 9 by 2 x to the power 1 by 2. Agree? So let's say, therefore, I'm not integrating, I'm writing this expression outside. Then I will integrate the simplified version. So let's simplify this outside the integral. 1 plus 9 by 2 x to the power 1 by 2 square. That is 1 plus 81x by 4. Okay, so you can maybe write 4 plus 81x, taking the LCM square root, right? So this will become 2. If I take the square root of 4 separately, then this will become 2, right? So this is your answer. So I can replace that in the formula. So therefore, my L is x is from 0 to 1. And I just found the value of this. So it is 4 plus 81x square root by 2 dx. Okay. So again, we use a substitution here. So this is what I was saying, that you can simplify this outside the integral. Okay. So you can simplify this outside first, and then you can just plug in the answer. It's your choice. In above example, we did everything inside the integral. It's not necessary that you do it inside or outside. So you can put this as u because that is inside the square root. I can write this outside because 1 over 2 can go out. So I just have this inside the square root 4 plus 81x. Okay, so we can replace this as u. If I replace this as u, then dx will become du with some constant times du. So that will be du will be 81, x is 1 and dx. So du by 81 will become dx. So see, dx will become du by 81, 1 by 81. And then you change the limits as well. If x is 0, u is 4. 4 plus 0 is 4. And when x is 1, u is 4 plus 81, which is 85. So I got 1 by 2. 0 gives you 4. And 1 gives you 85. And this becomes u. And dx becomes du by 81. So now I can also bring 81 outside. So this will become 1 over 81 into 2. 162, and this integration will become 3 by 2 divided by 3 by 2 from 4 to 85. So just replace 85 and then replace 4, you'll get the answer. Eighty-five power 3 by 2 minus 4 power 3. Okay, so whatever the answer is, you can write. So if you remember the formula, then it's not a difficult thing. It's just a practice with integration, writing appropriate formula and doing the practice with integration. So this was simple, nothing was difficult here in the arc length problem. Another thing is surface area. Area of surface of revolution. You see, we found in 6.2 and 6.3, we found the volume of solid of revolution. Recall in 6.2 plus 6.3, what we had an area problem. We had an area from A to B. Let's say this was the area between y is equal to fx and A to B. So this is the area. If I rotate this area about x-axis, then this whole area comes down here, right? So every point moves in a circle. So it gives you the solid of revolution. So because we are rotating the area, so everything inside is included. Everything inside is included, right? So we are getting the volume inside, right? So this is the volume inside. Blue thing is a volume, right? And the black, the whole thing becomes the solid. It's a solid in 3D. So we call it a solid of revolution. Solid of revolution. So we found the area of solid of revolution, volume of solid of revolution in 6.2. But if I do not rotate the area, if I only rotate the curve, if I only rotate the curve, not the area from A to B, then I will only get the outer portion, right? I will still get a solid, but just the outer part of it. Inside will not be included, right? Just the outside boundary, just this thing, right? So it is outside of the cup, basically. Whatever cup we are getting, let's say this type of cup we got, right? We got a cup type thing. So volume is inside, right? Volume is inside, which is coming from here. And this outer surface, if you want to find the area of this outer thing only, the outer part, this outer part, right? If you want to see what is this outer part, that is your area of surface, or you can call it the surface area. The outer thing is surface area, or the area of surface of revolution. Got it? So this is the difference between 6.23 and 6.5. That's why you see now we are using this outer length of the curve, and rotating that. Here what we had the area inside, and we rotated this area, right? We rotated this area and I got the inside volume of the solid. Here I'm only rotating the outside length of the curve. So I'm only getting the outer region, outer surface of the solid. Okay, so that is here now in 6.5. So what is the problem? You look at here. Suppose that f is a smooth non-negative function and the surface of revolution is generated by revolving the portion of the curve. You see the portion of the curve, not the area now, about the x-axis, right? Then the outer, this is the S, this is S, your outer thing, this outer, not inside, not inside volume, okay? Just the outer part, just the outer surface. So the volume here is this. So we can write this one here. I can just keep this definition and just use the formula directly. I just have to see what is my function and what are the limits. So let me write that here. So this is basically our formula. F is a smooth curve. So non-negative above x-axis. Then the surface S is generated by revolving the portion of a curve y is equal to fx between a and b is given by 2 pi fx, and this is the length of the curve. So see, when I had this volume, you see what we did, if you recall in 6.2, if you recall this volume, we said that take any value x here, then this is the line that is rotating. So it gives me the disk inside. This gives me the area of the disk, right? So what is the radius? Radius is f of x. This radius is f of x. So how we got at any point x, we said pi fx square is the area of the circle. And now this is not only one x. X starts from a and going to b. So I will integrate it from a to b dx. So this was the formula for the volume. I want to do the same thing. You see here, I'm taking x, but now at x, I'm not rotating this line. Inside is not included. I'm only rotating this point. So this will give me the outer circumference of the circle, not the inside area of this disk, right? Here, this was the area of the disk. So this outer circumference of the circle is given by 2 pi r, but the radius is still, see, the radius is still the height of the function fx. So it is 2 pi fx. 2 pi r was the circumference of the circle. And I have to add all these circles from A to B. But you see, when x moves to the left, I am getting these points on the line. And these points are the ds. This point is the ds, not dx only. All right. So what we are doing, we are using the length of the curve. So I have to integrate this 2 pi x. So my formula should become this. My formula should be 2 pi fx circumference with ds from A to B. We are not only integrating dx now, ds, and the formula for ds was this. If you remember, the formula for ds was this. 1 plus dy by dx squared. That's why they did not discuss the surface of revolution before 6.4. They did 6.4. They got the arc length, the portion of the arc length, and now we are using that. Here we had the disk, area of the disk, but at every x we are getting the area of the disk just by pi fx square. So we only integrated with respect to x. Here I am getting the circumference of the circle, but that circumference, the tip is moving from ds, not from dx. So that's the reason we have this arc length You see the formula from the arc length is there. Okay, so that is the surface of revolution. So let's see if I do an example. Find the area of the surface of revolution. Copy this here. If you want, you can copy this as well. It will give you a good sense. Right, so this is our graph. So x, this is x-axis, this is y-axis. So you are rotating this curve. You are just rotating this curve, right, about x-axis. So I got, you see, everywhere I'm getting a circle. So if you take any x here, then x goes towards 0 on the left and towards 1 on the right, right? So these are the limits of x. But at every point, I need ds that is rotating, right? So I need area of a surface of revolution. So anyway, we just have to see what is my function. So here my function is x cubed, right? So x goes from 0 and 1, between 0 and 1. So it means my a is 0 and b is 1. So I can just replace everything in the formula. So therefore, the surface area is from 0 to 1, 2 pi fx, which is x cubed, into 1 plus f prime x squared. So I can find f prime x. F prime is 3x squared. So 1 plus 3x square whole square dx. So see in the formula, if you look at the formula here, right? So 2 pi fx. So I got this fx here, and 1 plus fx f prime x squared. So this is f prime. So this is my f and this is my f prime. Okay. And x goes from a to b. So a and b are from 0 to 1. So now I will simplify and solve. 2 pi is a constant. I can write it outside. X cube inside, and here it is 1 plus 9x4 dx. Now you see, 1 plus 9x4 has the derivative x cubed, right? So I can substitute. I can use this substitution. So see, that's why we went through chapter 5, because chapter 5 was in calculus 1. But I went through chapter 5. The reason is I will need these techniques of integration here in chapter 6. That's why I reviewed chapter 5 and we did this substitution method. 5.3 and 5.8 or 9, I guess, had this substitution. So substitution is 1 plus 9x4. So how we do the substitution? We have to look at a function inside some other function whose derivative is given with dx. This is basically the idea. Then we substitute gx is u is equal to gx. Then we substitute u is equal to gx because the derivative of gx is given. So here, if this is my u, then the derivative of u is x cubed, which is given here outside with dx. Of course, we can write them together. No issues. So now you see the du will be 9 into 4x cubed. You can say that the derivative is not x cubed. Derivative is 36x cubed. But I'm only interested in the variable part. 36 is not a problem. 36x cubed dx. I don't want 36 here, so no problem. I can send it with constant is not an issue. Okay, so this will become 2 pi square root of u x cube with du. These both will become du by 36. So x cube and dx, they both are gone together, right? Together they become du by 36. So now the limits. If x is now the limits, if x is 0, my u is 1 plus 9 into 0 to the power 4. So that is 1. And when x is 1, u is 1 plus 9 into 1 to the power 4. So that is 10. So my u goes from 0 to 10. Now if I integrate this 36, I can write it outside. 2 pi by 36. Square root of u will become u to the power 3 by 2 over 3 by 2 from 1 to 10. So again, 3 by 2 can also be taken outside. 2 pi by 36. 2 pi by 36 is pi by 18, right? 2, 18 or 36. So, and then I can write 2 by 3 outside. And when you replace 10, first 10 to the power 3 by 2, then minus 1. So that will become 1 to the power 3 by 2. So the answer will become 2 9s are 18, 9 3s are 27. So pi by 27, 10 to the power 3 by 2 minus 1. So you can leave your answer like that. But if you use calculator, you can write the number for that. Let's see what is the answer. 10 to the power 3 by 2 minus 1 into pi by 27. The same answer. And if you use calculator, it is 3.56. 3.56. You can stop here as well, no issue. This is also an answer, no problem. Okay. So see, it's not, if you know the formula, then it's not difficult. You just have to use the appropriate formula. We can also do it with respect to y-axis as well. Let's say if the limits instead of x, they say rotate it about y-axis. If they rotate it about y-axis, then of course I can change my formula like the arc length formula, right? We can easily change if x is equal to gy, right? Is revolved. Now I will not write it, even if they write y is equal to gx, if they say this one, but I will write x is equal to gy. I will find x in terms of y is revolved about y-axis, right? Then my surface area will become c to d 2 pi gy now, not fx. And you know, it will become 1 plus g prime y square. This was the arc length with respect to y. So everything will be replaced with y. Instead of x, you will get y, y, y here. And the limits also for y. So y goes, instead of fx, you got gy, g prime of y dy, and y goes from 0 to infinity. So what we are doing, any curve that is given here, x is equal to g of y. Sorry about that. And we are rotating it about y-axis. So this curve will come here, right? And you will get this type of surface. This type of surface. So now I will take y goes from C to D. Y goes from C to D. But if I take any y here, these are the limits of y. But at any y, I still need the circumference of this circle. But now the radius of this circle is x, which is gy, not y, which is gx. This is the radius now. Okay, that's why we got this gy here, the radius. So this is an example where they gave me the problem where the revolution is about y-axis, right? Find the area of the surface generated by revolving the portion about y-axis. Now see, this is y-axis now. But they did not write these as y. They wrote this as it is, like in the previous example. But I will change it. I will change it to x is equal to g of y. And here I need the values of y. I need y here and I need x is equal to g of y, right? So here I need x is equal to g of y, which will become square root of y. And here y values. So I will see what are the y values. Anyway, if you want, I can copy the picture as well, the figure as well, because figure also help us a lot in understanding the things. right? So now we are rotating about y-axis. So I need this value of y. Y is 1. In the picture it is given, and this is 4. But I can find this y by plugging these values here. You see, y is equal to 1. When x is 1, y is 1 square, which is 1. And when x is 2, y is 2 square, which is 4. So see, y goes from 1 to y is equal to 4. But in the picture, if picture is not given, then I can find the values from the function. And this in terms of x, I need to write this in terms of x, which is square root of y. So now if I take any y here, then this is ds rotated about y-axis. So my radius is x, right? Radius is x, which is x is equal to square root of y. So my surface area will become y from 1 to 4, 2 pi gy, which is square root of y, into 1 plus the derivative. So what is the derivative dx by dy? So I can say that this is my gy here. So gy is square root of y, right? So g prime of y will become 1 over 2 square root of y. So 1 over 2 square root of y whole square dy. So see here, 2 pi square root of y and 1 plus 1 over 2 square root of pi whole square. So we, instead of getting fx, we got g prime, g and g prime. And y goes from 1 to 4. Y goes from 1 to 4. So now 2 pi is constant. 1 to 4 square root of y. Let's simplify this. 1 plus 1 over 4y dy. So see here, these both are in square root. So I can bring this y inside, right? In multiplication, if you have multiplication of a into b, I can write it in one root. I can multiply a with b. So the same thing I am doing, I am multiplying y inside. We are not integrating yet. So y into 1 and y, when it multiplies with this one, y and y will cancel. So you got just 1 by 4. So again, you can take square u as y, but if you have just y plus a constant in square root, right, and you integrate, you don't even need to substitute. You can just uh, use the power rule. We can do that. So this will become 2 pi y plus 1 by 4 to the power 3 by 2 divided by 3 by 2 and from 1 to 4. So this will become 2 by 3, so it will become 4 pi by 3. And if you put 4 in here, so this becomes 4 plus 1 over 4, 3 by 2 minus 1 plus 1 over 4, 3 by 2. Okay, so this is your answer. So here you can now check. Same thing, right? Pi by 4, 2 by 3, 17 minus 5. 17, 3 by 2, 5, 3 by 2. So this is 17 by 4. I think they have 4 outside. So let me simplify. But anyway, you can use calculator to simplify that. No issues. So that is 17 by 4. This is the 5 by 4. So that's why they are getting 17 and 5. But anyway, you can use calculator and get the answer. No issues. Okay, so see, we can use both x and y directions that we have been using from day one, you know. So I think let's see if I can attempt something from exercises. So first four questions are revolution about x-axis, and these are revolution about y-axis. So maybe we can pick one question from here. Can we pick this one? This may be a little difficult, but let's pick it. And then we can choose something from here as well. Or at least I can make it a, you know, integral, and then you can solve it, let's say. From 1 to 8, exercises from 1 to 4, and 5 to 8 on page page number is 447. So these are revolution about x-axis, and these are revolution about y-axis. So we can pick one from both. And let's see. So let's say exercise 3, I said, right? So exercise 3 was y is equal to 4 minus x square and x from -1 to 1. And x interval is given from -1 to 1. So it means your a is -1, right? This is your b, and this is your fx. And fx is 4 minus x square. You don't have to write fx, because let's say you can write the formula as s is equal to a to b 2 pi fx. Fx is y, and 1 plus dy by dx square, f prime x. If you want, you can write this formula and keep y as it is. No need to write f of x. So from here, I need dy by dx. So dy by dx is 1 over 2 square root of 4 minus x square into minus 2x. So this 2 and 2 cancels. So this is, we can put y here and dy by dx. And don't leave y as it is. When we write formula like this, I saw students make mistake and they keep y as it is. You cannot keep y as it is, because we are integrating with respect to x. So everything should be replaced by x. So it means y should be replaced by the right hand side, a function of x. So therefore, my s will become -1 to 1, 2 pi y. Y is 4 minus x square, which is fx, into square root of 1 plus dy by dx. Dy by dx is minus x over 4 minus x square, right? Into dx. This may become little difficult, but let's simplify. Hopefully, after simplification, this integral will not be difficult. So let's simplify this. It becomes 1 plus x square, because minus x square is x square, divided by 4 minus x square. Square root will be cancelled in the denominator. And now take LCM. If you take LCM, you can multiply this here with 1 and then add x square and divide it by this. So if we do this, 2 pi -1 to 1, 4 minus x square. So I got 4 minus x square plus x square. 4 minus x square into 1 is 4 minus x square, and plus x square and divided by 4 minus x square. This is my LCM, right? Dx. So see, this is cancelled with this. So it becomes very easy, and x square is also cancelled with x square. So 2 pi, I only had square root of 4 inside. Square root of 4 dx. See how easy it is. Square root of 4 is 2. So that is also a constant, just a constant. So 2 will go outside, it will become 4 pi, and integral of 1 is x from -1 to 1. So 4 pi into 1 minus -1, which is 2. So the answer is 8 pi. So see, it was looking very bad at the beginning here, you see. At this step, it was looking hard, right? But after simplification, now you see, when I did not integrate, I simplified the inside and I end up getting just a constant. Very easy. So maybe it looks hard at the beginning, but after simplification, it becomes very simple. So let's see what is the answer. Exercise 3, 6.5 or 71. 6.5 exercise 3. Six point five. 6.5 exercise 3. 8 pi. Right? So this is answer is correct. Agree? So in a similar fashion, you can do one problem. Let's say I can make you an integral. Let's say 5. Right? So in 5, x should be given in terms of y. Even if y is given, we have to write it in terms of x. So here. So x is 9y plus 1, 0 to 2. Y is from 0 to 2. So from here now, my formula is from C to D, 2 pi x and 1 plus dx by dy square and dy. And this x is also a function of y. That's why we have dx by dy. So this is that. Okay, so this x is not just x. Don't leave it as it is, because you are integrating with respect to y. So everything should be in terms of y. So that is what I will replace here. So anyway, I need dx by dy. The derivative of this with respect to y is just 9. So therefore, my s will become from c to d, the values of y, 2 pi x. X is 9y plus 1 into square root of 1 plus dy by dx square into dy. Dx by dy square. And this is a constant. 9 square is 81 plus 182. Square root of 82 is constant. I can bring it outside. So 2 square root of 82 and pi. 2 pi and square root of 82, they are outside. And inside, we are left with only 9y plus 1. So again, very simple integration. 82 is 41 times 2. But is it anyway, if there is any simplification, you can do that. So 2 into square root of 82. 23 into 4. No. 23, 13. No, this is the 92, not 82. So we leave it. So now the integral is 9y squared by 2 plus y. 9y becomes y squared by 2 and 1 becomes y, right? So 0 to 2. Now you can replace 2 first and then 0. Pi is also there. Pi and 9 y square 4 by 2. 9 into 2 square by 2 plus 2 and 0 will give you 0. So that's my answer. So if you simplify, you will get something here. 9 twos are 18 plus 2, 20. So that will become 20 inside. So you can simplify and see what is the answer. If you want me to check the answer, I can check that. And then again, it's question number 6 of the same exercise. Here. 40 pi 82. See, same answer. So they did not simplify using calculator, right? 40 pi 60. So see, 20 times 2 is 40. 40 pi and square root of 82. So the same answer. But you can use calculator. This is not approximate. This is equal. But if you want, you can use calculator and write the approximate answer if you want. Otherwise, leaving it here is also fine. All right. So I hope this is completely understood. So go through that and try to do some exercises. I did a couple of them. So you try the other ones and do some practice with it. Hopefully everything will be okay. So if you have any questions, you can ask. Otherwise, I think I'm done. Let me stop the recording here.